Thanks, Anjana, for your kind introduction. And thank you and the other organizers for giving me the chance to talk at this great workshop. It's really been a pleasure to listen to the talks yesterday and today. And yeah, I'm looking forward to the next ones. So as I said, like today, I'm going to discuss about these new results that we got together with Ligao, who recently moved to Munich. And the results are available on the archive as of today. And I think hopefully they will nicely fit with some of the topics that we have heard yesterday, and especially with Angela's talk just before. And so we saw this notion of complete modified logarithmic Sobolev inequalities, for which traditional techniques to prove the existence of the constant seem to fail in general. And I hope I can convince you here that there are some very simple arguments that you can use to answer the question of the existence of the constant, and which might hopefully lead to interesting new applications. Okay, so without any transition, I introduced the relative entropy, which we saw so many times so far. And in my talk, I will just consider states that act on the finite dimensional algebra of n by n complex matrices. And as we all know, this relative entropy satisfies this notion of data processing, which by this I mean that it's basically monotone under the action of a channel. And so one natural question that directly pops up from this inequality is whether there is a good way to quantify the amount of loss of information in some sense, or the amount by which the relative entropy decreases after the action of this channel. So the question is whether you can basically find a constant eta, which I will call a contraction coefficient, that only depends on the channel, and such that this is going to be strictly less than 1. And it's a very basic question. And classically, there are plenty of methods to quantify, or to at least to estimate this constant, which I provide here. So these are the ones that I know of, at least. However, I think, without making a mistake, that any of these methods fail to some extent when you try to deal with quantum systems. So I would like to tackle perhaps a slightly easier question in this talk. So in this case, the state sigma on the second slot of the relative entropy that I'm taking will be the state towards which the first slot will converge to in the limit of many applications of my channel. So to make things more rigorously, I'm basically considering this Jordan decomposition of the channel phi, which has this nilpotent part. So this is the part that will vanish in the limit of many applications. And this is the part that is basically projecting onto the peripheral spectrum of the map phi. So if I define the projection as En, then I know that, for instance, in one-to-one norm, this limit occurs. And now the question is how fast does this convergence takes place? And the sort of easy way to answer the question will be to consider the spectral gap of my channel. However, in many situations of relevance, the gap will provide with a very bad estimate, and you know that you can achieve better bounds in general. And that's sort of the reason why people consider sort of stronger topologies to answer this question. And the one that we consider here is the topology given by this so-called sort of topology given by the relative entropy. So I want to consider this contraction coefficient S of phi for which this inequality holds for some S of phi that hopefully will be strictly less than 1. And the good thing about the classical case is that these contraction coefficients have this property of tensorization. So we already discussed this many times in the previous talks, which basically means that if you look at the tensor product of channels, then the constant for the tensor product will be controlled by the maximum of the constants for each of the single channels separately. But this property now is known not to hold in the quantum setting. And this is why people consider so-called stronger versions, complete versions of the inequality, where instead of looking at the contraction provided by the map, you look at the contraction provided by the map tensored with the identity on an arbitrary large reference system. So I want to basically consider this contraction coefficient SC, or complete SDPI constant, for which this inequality holds for all arbitrarily large reference system and for all states on your system where the channel acts and this reference system. And so the question is whether we can prove in high generality that this SC constant is strictly less than 1. Okay. So it's often useful, I think, to consider the continuous time regime where this channel phi is generated by some Lindbladian, as we saw in Angela's talk. And in this case, the contraction coefficient that we want to have is something that will exponentially decay to 0 in time. and with a rate of convergence that is given by this alpha c. So this alpha c is what we call the complete modified logarithmic Sobolev inequality constant, or CMLSI constant in short. And it turns out that it satisfies this derivative of the first inequality with respect to time, where on the right-hand side, you have the so-called entropy production of my generator, which is this derivative of the relative entropy alongside the semigroup. Okay, so this inequality was very, very much considered in the primitive case. So when you have only one fixed point of your evolution towards which you are sure to converge, and in the non-complete setting, and there we can actually use some classical estimates in order to control the constant. However, if you want to consider non-primitive semigroups, and even more so if you want to consider complete MLSI, then general results are still lacking. So what is known so far is that, and this is actually was proven in the first paper considering this, which considered these inequalities, is that in the case of a symmetric quantum Markov semigroup, or QMS, those quantum Markov semigroups for which the constant is strictly positive, it will be dense in the set of all QMS for a given fixed dimension. And you can actually make this slightly more general statement by considering QMS, which are reversible with respect to some other state than the maximum mixed state. But what I want to prove here is that actually the constant will always be positive in finite dimensions under this detailed balance condition on reversibility. Okay, so here's the overview for the rest of my talk. I will first present a very simple key lemma, which will allow me to control relative entropies between two quantum states in terms of Fisher informations in both directions. So I will explain what I mean by Fisher information in a second. And I will use these key tools in order to prove the existence of the CMLSI constant under this detailed balance condition in finite dimensions, as well as the existence of the CSDPI constant, also under a detailed balance condition. Okay, so we already saw the relative entropy, so I will not take more time on this. And the second sort of suspect here is the Fisher information. So the Fisher information, you can think of this, so this is in the Kubo-Mori-Bogolubov sense. You can think of this as providing the manifold of full rank quantum states with a remaining metric, where the metric is taken at the point sigma of your manifold. And this observable gamma, you can think of it as a tangent vector that provides some direction to your vector field. And if everything commutes, then you get back the usual classical Fisher information in the discrete setting, where Q is just a property mass function here. And it turns out that these two quantities are very much connected to each other in the sense that the Fisher information at the point gamma along the direction, at the point sigma along the direction gamma is the Hessian of my relative entropy at the same point and along the same direction. Okay, so in the next part of the talk, I want to introduce this tool that we are using extensively in this paper. And for this, I need to introduce one last relative entropy quantity that will play a big role in the talk, which is this Dmax between, so the maximum relative entropy between quantum states rho and sigma. And you can think of this as the best constant, the logarithm of the best constant for which this inequality holds for the states rho and sigma in a semi-definite order. Okay, so with this definition, we can prove the following very simple lemma. So the first inequality is not even a lemma; it's really just by definition of these Fisher informations almost. So if you just relax the condition of A and B to be states, so if you just look at A and B to be positive definite matrices, such that A is less than B, then you have a reverse order for the Fisher information. So the Fisher information of some vector fields or some tangent vector gamma at the point A will be greater than the Fisher information of the same tangent vector at the point B. And the proof is really just by looking at the definition. So you just use basically the operator anti-monotonicity of the inverse function to go from A to B. So there's nothing else than that here. And the second part of the lemma allows me, as I said, to control the Fisher information of rho minus sigma taken at the point sigma in terms of the relative entropy of rho and sigma in both sides, where on the right-hand side here, we also have to consider this function of the exponential of Dmax. Okay, and the proof of this is also pretty simple. I'm not even claiming that this was not known, at least the left-hand side was already known. And so the point is to use this interpolation, this linear interpolation between the state rho and the state sigma, so which I denote by rho of t. And then I consider this function f of t, which is the relative entropy between rho of t and sigma. So at time t equals to 0, since rho of 0 is equal to sigma, f naught will be equal to 0. And you can also prove that the derivative at 0 will be 0. So then f of t, or even f of 1, which is the relative entropy that we want to control, will be just given in terms of this double integral of the second derivative. And as I mentioned before, this Fisher information is the Hessian of the relative entropy. So it's not surprising that you end up with this expression for f second, which is this Fisher information of rho minus sigma taken at the point rho of t. And now, so what I want to do is to control this guy in terms of the same Fisher information, but taken at the point sigma. And to do this, I just control the state rho of t itself in terms of sigma, where on the right-hand side, you see that this kappa comes up. And doing this, then you can use the first inequality in order to further control these Fisher informations. And then if you reintegrate this function, you get back the result. Okay, so next I would like to show you how you can use this sort of bounds to prove the positivity of this complete MLSI constant for reversible quantum Markov semigroups. And the notion of reversibility that I'm going to use here is with respect to the so-called GNS inner product. So I will assume that my semigroup of channels in the Heisenberg picture, hence this star here, will satisfy this symmetric relation with respect to some full rank invariant state sigma. So let's just consider for a while what we know about the MLSI constant in the primitive setting. So not the complete MLSI, just the MLSI itself. And to have a way to control the constant, the sort of natural way to do it is to go through hypercontractivity. So hypercontractivity is this notion that tells you that the Heisenberg dual of my channel will contract from L2 spaces to LP of t spaces for some p of t that has to be smaller than this sort of maximum value, which is 1 plus this exponential. And you see it is controlled by this parameter alpha 2, which is usually called the log-Sobolev inequality constant. And since we are controlling LP norms, you can use some easy interpolation methods to get this sort of worst case bound on alpha 2 in finite dimensions, which will depend on the gap of your generator and the minimum eigenvalue of your invariant state. And then under the condition of GNS symmetry, you can actually use some discrete differential calculus to further bound alpha 1 or the MLSI constant in terms of the LSI2 constant. And if you use those two inequalities together, then this gives you a non-zero bound, a positive bound on alpha. So I think that the kind of natural question to ask from here is whether the notion of hypercontractivity could be itself extended to the complete and non-primitive settings. And this was a very promising path that was taken by Beggy and King a few years ago. However, we proved afterwards with Yvan Bardet, and there is also another work by Marius and Ligao and Nicolas Raquente who have some other proof. We proved that the complete LSI2 constant that you would end up with will inevitably be equal to 0. So in other words, this will not provide you with any relevant lower bound on the alpha 1 constant. Okay, so we have to come up with some other way to prove the positivity of the CMLSI constant. And to do this, let me introduce this Dmax quantity between two algebras. So we already discussed what the Dmax is for two states, and you can sort of lift this to a Dmax between algebras. So Mn for me will be just the matrix algebra where my semigroup acts, and N is the fixed points of my semigroup. And I define this Dmax as the maximum distance as measured in maximum relative entropy between a state rho and its projection onto the fixed points. So this basically tells me that for any state rho, I can control it by its production up to this the exponential of the Dmax. And actually, this quantity was already introduced and studied already in the 80s, and it was called the Pimsner-Popa index, at least in the tracial case. And more recently, a completely bounded version of this constant also was studied by Gao, Junger, and Laracuente, where you just basically tensorize your algebra with an arbitrarily large matrix algebra MK here. So the other sort of quantity that will come up and that we already saw is the gap of my generator. And it satisfies this so-called variational formulation of Poincaré inequality, where on the left-hand side, you have the Fisher information of rho minus its projection onto the fixed points. And this Fisher information is taken in in En of rho. And on the right-hand side, you have the Dirichlet form of rho, which is minus this inner product between rho and L of rho, again taken in this Fisher information metric at the point En of rho. Okay, so here's our first theorem. So we find this lower bound on alpha c, on the complete MLSI constant that depends on these two parameters, which I just introduced. And I just remind you of the inequality that we are trying to prove, where on the right-hand side, we have this entropy production, which I expressed as follows. So if you take the derivative of the left-hand side, basically you end up with this quantity here. And so as a corollary, we prove that for matrix algebras and under this condition of detail balance, we have a positivity of alpha c, and this provides us with another proof of this result. We already saw the first proof that we saw was yesterday with the talk of Hao Zhang, and this is another way of doing it. Okay, so as for the proof, just to give you the idea, I will restrict myself to the case where L is symmetric. So it's going to satisfy this detail balance condition, but with respect to the maximum mixed state or the identity matrix. And in this case, we know that the generator has this nice expression. So you can think of it as a Laplacian, basically, which is a sum of second derivatives of a sum of second order partial derivatives, where for each I here, you're just taking the commutator of your state with a Limblad operator, Li. So now the first thing I will do will be to control this Dirichlet form in terms of the entropy production. And to do this, I just rewrite the expression that we had before for the entropy production. Then you can use integration by parts to put one of those partial derivatives on the other side of the trace. And then you can use some non-commutative differential calculus to further write the derivative of the log of rho in terms of the derivative of rho divided by rho. And of course, in the non-commutative setting, you have to be careful what you mean by differentiating, by taking ratios, but basically what you end up with is this kernel, which we already saw, because this is the kernel that defines the Fisher information. So in the end, we have that the entropy production of rho is equal to the sum over all these directions given by these Limblad operators of this Fisher information of the partial derivative of rho taken at the point rho. And similarly, you can also write the Dirichlet form in terms of a sum of Fisher informations. And again, you can use this integration by parts to put one of those partial derivatives on the other side of this inner product. And you end up with this quantity where the only difference with the previous one is that you're taking the Fisher information at a different point. But you can actually control one thanks to the other, using this first very simple observation that I made in my technical lemma. So when A is less than B, I know that the Fisher information with respect to A will be greater than the one with respect to B. And if I take A to be the state rho and B to be its projection onto the fixed point times its Pinzner-Popper index, I end up with the following upper bound. And now if I use the second part of our key lemma, I can further control the relative entropy in terms of the Fisher information. Then I can use Poincaré inequality to control this term in terms of the Dirichlet form. And finally, I can use the upper bound that I derived here to control everything in terms of the entropy production. So in the end, we prove the CMLSI because these are the outer bounds are basically what the inequalities is made of. Okay, so I would like to just briefly explain how we can further bound these indices. So in the case of a tracial condition expectation, so if one of the invariant states is the maximum mixed state, basically, you can actually have an expression for this Pinzner-Popper index in terms of the multiplicities in the direct sum decomposition of your fixed point algebra. And so this is the expression that you end up with. And if you consider, if you want to actually have, if you want to consider semigroups that converge to something else in the maximum mixed state, then you can still control this Pinzner-Popper index as at the cost of having to add this minimum eigenvalue of sigma to the power of -1. So if we use these bounds into our theorem, we get the following lower bound for alpha c, which is itself a lower bound on alpha by definition. And we can now compare this in the case of primitive quantum Markov semigroups to what you would get if you were to consider the hypercontractibility estimates for alpha. And you can see that our bound is much worse. It scales really badly with the dimension, but I'm not claiming here that this is a good bound. I mean, actually, even this bound is really very bad. But the point is that we have an existence result now. And it works also for non-primitive and in the complete setting. Okay, so I think I won't have much time to explain how to prove the case of the complete SDPI constant, but we can basically run similar arguments. Again, I have to assume that my channels satisfy this detailed balance condition. And under this condition, we can prove that this complete strong data processing inequality constant is upper bounded by this function of the Pimster-Popper index as well as the gap of my channel, which is going to be strictly less than 1. So I will just skip the proof, I think, sorry. So just to wrap up, we have shown the existence of the complete MLSI and the complete SDPI constants under this detailed balance condition. And the kind of key technical tool is to find ways to control the relative entropy in terms of fission formations. And I didn't mention this here, but we also proved the existence of the complete approximate tensorization without this additive error term. So if you remember what Andrea was discussing in her talk, we can get rid of this additive term, but at the cost of having this multiplicative error term that is scaling really badly, in the sense that we don't recover strong sub-additivity in the case of, if your condition expectations are partial traces. So we are still working on trying to improve this result. And I will just conclude with this open problem. So as you see, we've shown that this alpha C constant exists. And I think from now on, it would be very interesting to see if we can find some approximation techniques, perhaps coming from optimization theory. So I believe there will be a talk on this subject on Thursday by Hamza Fawzi, where he considers using this optimization theory to find approximations on the LSI2 constant for classical Markov semigroups. And I just wonder if we can also lift their results to this complete setting. It would be nice to see if this works as well. Okay, so with that, I would like to thank you for your attention, and we'd be happy to take any question.